And welcome back. The king of the internet. That is me, in case you didn't know. So I hope everyone's doing well. So what we're gonna be doing today is that we're gonna be doing a day 11, part 1 of Jeremy's Tech Lab stuff for CCNA. If you're not already subscribed, you should definitely subscribe to this channel. He is amazing and he is teaching me so much. So what we're going to do is we're going to go through part 1 of day 11, and then we're going to do part 1, day 11 of the packet tracer. And we're going to kind of see where we are and how we feel about that. And if we have enough energy and we have enough time, then we'll do day 11 part 2. But these videos are pretty big. This one is 30 minutes long. The other video is 38 minutes long. I am going to play it at probably 1.5, maybe even 1.25, maybe even 1.5 speed. So we'll just kind of see what we're doing. We are also going to do a little bit of practicing of subnets, and of course we have the Anki cards, which is everyone's favorites. Those cards help out a lot, but god damn do they suck. Oh my god, dude, nothing's worse than just doing flashcards. But we'll take some breaks and do some things in between, so that way it's not like we're doing all the flashcards at once. I think in the past some of the problems have been is that I try to do the flashcards all at the end instead of maybe doing them like a little bit in between and things like that. Okay, so anyway, I also have my handy dandy little assistant here to kind of help us through things if we get stuck and have very niche, very specific, odd, curious questions about stuff, so we can go down a rabbit hole. Anyway, that's what we're doing, and we're gonna go ahead. We're gonna dive directly into it. So let's do it.
Welcome to Jeremy's IT Lab. This is a complete course for the CCNA, Cisco Certified Network Associate exam. In this video, we will cover routing fundamentals, a very important topic to understand for the CCNA exam. In the Ethernet LAN switching videos, we looked at how switches forward frames to their proper destination. The process routers use to forward packets to their proper destination is different, and that's what we'll look at in this video. Here's what we'll cover in this video. First, I'll answer the question, what is routing? Then we'll look at the routing table on a Cisco router. Switches have MAC address tables, and routers have routing tables. It's very important that you know how to read a router's routing table. Specifically, we will look at two types of routes. So
basically, we're kind of going up the OSI model. We started with layer 2 with like switches and MAC addresses and stuff, and now we are at layer 3, which is routers, routing tables, and all that good stuff.
Found in a routing table, connected and local routes. We will also look at routing fundamentals, specifically route selection. In a router's routing table, they will usually have a variety of routes. So how does the router select the correct route for a packet? We'll discuss that in this video. I want to emphasize that this lesson is extremely important for the CCNA and for learning networking in general, and so is the next video. So take it step by step, take notes, and ask questions if you need help.
Yeah,
After covering all of the material, I will also show a one-slide review of everything in this video. So I hope that will help you review and remember what you learn. Let's get started. So, what is routing? Well, when a router receives a packet, it's the router's job to forward it, to send it to the correct destination. That's where routing comes in. Routing is the process that routers use to determine the path that IP packets should take over a network to reach their destination. And routers store routes to all of their known destinations in a routing table, which we'll look at soon. As I mentioned before, switches keep a MAC address table with their known destination MAC addresses, and routers keep a routing table with their known destination networks. When routers receive packets, they look in the routing table to find the best routes to forward that packet. There are two main routing methods that routers use to learn routes. One is dynamic routing, in which routers use dynamic routing protocols such as OSPF to share routing information with each other automatically and build their routing tables. We will cover dynamic routing protocols such as OSPF later in the course. Another type is static routing. In this case, a network engineer or admin manually configures routes on the router. We will cover static routing in the next video. In this video, we're going to cover a kind of route that doesn't fit into either category. Now, what exactly is a route? Basically, it's an instruction to the router. A route tells the router, to send a packet to destination X, you should send the packet to next hop Y, and next hop means the next router in the path to the destination.
Yes.
Or if the destination is directly connected to the router, send the packet directly to the destination. Or if the destination is the router's own IP address, receive the packet for yourself, don't forward it. This is how the routing table works. It's a set of instructions like this. To demonstrate routing in this video and the next one, we will use this example.
Okay, that makes sense. So every hop And then it wants the shortest path possible. So in this instance, both paths to go to PC4 are the same.
Network. Actually, in this video, we will only look at one small part of this network. In the next video, we will use the entire network. But first, let me introduce the network. There are 4 routers connected together, and they represent a WAN. WAN stands for Wide Area Network, a network that extends over a large geographical area. For example, each of these 4 routers could be in different cities or even different countries.
To the WAN show.
And then, connected to R1 and R4, there are 2 LANs, local area networks. I'm only showing one PC at each LAN, but let's say each of these LANs is a different office in a different city, so really there are more hosts in each LAN. R2 and R3 probably should have their own connected LANs too, but just to keep the diagram a bit cleaner, I'm not showing them here. Now let's look at the IP addresses each device will be using. For this LAN connected to R1, the network is 192.168.1.0/24, and R1's G02 interface IP is .1, and PC1's IP is .10. Then this WAN connection between R1 and R2 is 12.0/24. R1 G01's IP is .1, and R2 G00's IP is .2. This WAN connection between R1 and R3 is 13.0/24, with R1 G0.
Yeah, because each one of these ports is going to have their own IP address. It's going to have their, because they're all default gateways. So G01 of R1 will have its own, and G00 of R1 will have its own. But now my question is this IP address going to be the same as this IP address? Because I thought it was the port.
00 as .1 and R3 G00 as .3. The WAN connection between R2 and R4 is 24.0/24, with R2 G01 as .2 and R4 G00 as .4. Then the final WAN connection between R3 and R4.
Okay, that's worth clarifying. When I have, let's say 4 routers connected, is it the port G/00 we'll say 4 that gets the IP address, or is it the connection itself that gets the IP address? For example, if R1 is connected to R2, what he has it 0000, and the cable is connected to G0/0 on both routers. Do both router ports get the same IP address, or do they have different ones? And or is it that the connection itself is the IP address? Well, there's no way. It has to have different ones, because, like, what if this is my house and what if this is my friend's house? There's no way that those are going to be the same. Okay, well, we're going to let that cook there for a second.
Is 34.0/24, with R3 G01 as .3 and R4 G01 as .4. Then the LAN connected to R4's G02 interface is 192.168.4.0/24, with R4 G02 as .4 and PC4 as .10. Notice that I made all of the router IP addresses the same as their name. All of R1's IP addresses are .1, R2's IP addresses are .2, R3's are .3, etc. Don't expect IP addresses like this in real networks, but in lessons and labs, I will often use simple addressing schemes like this to make it easier to understand. In the next video, we will configure static routes on the routers to allow PC1 and PC4 to communicate with each other over the network.
Static routes
This video will focus on 2 types of routes automatically added to a router's routing table, not dynamic routes or static routes.
I see here.
The router port's interfaces get the IP addresses. The cable connection itself does not get an IP address.
See, that's what I
So
thought.
if R1 Geo0th, cable, Geo0th R2, then both router interfaces need different IP addresses, but those IP addresses must be in the same subnet. Example, R1G 00th equal to 1.0.1 2.130. R2G 0th equal 0.1 2.2. They are different IP addresses, but they belong to the same network. 1.0.1 2.0.
Okay. But they don't, obviously they don't have to belong to the same network, because if I'm trying to get to my friend, there's no way he's going to be on the same network in his house.
2. Analogy. Think of the cable between routers like a street. The street itself has a name, 1.0.1 2.0, 30 network. But the houses on the street have individual addresses. R1 house equal to 1.2.1, 2.1. R2 house equal to 1.0.1 2.2. The street is not one house. The street is the shared network. Each device connected to that street needs its own unique address. So the link is like the street, and the router interfaces are like the houses on that street. 3. More in-depth explanation. On a router, each physical or logical interface can be assigned an IP address.
Okay, so
Examples of router interfaces. Gigabyte Ethernet 0/0. Each router interface is its own layer 3 connection point. So when R1 connects to R2, you are really connecting. R1's J00th interface to R2's J00th interface. Each side needs its own IP address. Example, R1 connected to R2. Use this subnet.
Okay. So there's a subnet. That subnet gives you these addresses, the purpose, the network address. There's this, there's that, the two defaults, and then the broadcast. So the configuration would be interface G00, IP address would be, the range would be this, no shutdown. Of course, no shutdown. Important rule.
1.0. For router-to-router links, each router interface gets its own unique IP address, and both addresses must be in the same subnet. Wrong? R1G 00's wrong. R1G 00th 1.0. Correct. R1G 00th equal to 1.0.1.
Why? Because R2 is connected to two different networks. Wait, each connection should usually have its own subnet. Example, R1 to R2 is this. First router, second router. Okay, that makes sense. Because it's saying that it has to be on the same network. Okay, that makes sense if I'm like within my own private stuff, but like, how does that work if I'm trying to go out into the world? Think faster, chatbot GPT. Faster. There we go.
When your house talks to your friend's house, your devices are not directly connected to each other on the same network. Your house has its own private network. Your PC, 192.16.8.1.5. Your router, 192.16.8.1.1.
Okay.
Your friend has their own private network, friend.1.1, because they are hidden behind different home routers. The communication goes through the routers. Your PC, your router, your ISP, internet, friend's ISP, friend's router.
So does the ISP have its own like set of rules and stuff because it's all public? Is my default gateway to my house not a public IP address? Is my entire house network just within a much larger private network that is linked to the ISP, and the ISP have the public IP address? And what actually is my ISP actually my default gateway? I'm like, okay, hold on.
Friend's router, friend's, the big idea. Inside your house, your devices use private IPs. Across the internet, your router uses a public IP. Your friend's router also uses a public IP. 2. Analogy. Think of your home network like an apartment building. Inside your house, your devices have room numbers. PC equal. Your friend's house may also have a room 50, room 51, and room 52. That is okay, because they are in a totally different building. To send something from your house to your friend's house, you do not mail it to room 50. That would be meaningless globally. You mail it to the friend's street address first. Their router is like the front desk. Then the router decides which internal room device should receive it. So, 3. More in-depth explanation. Let's say your computer has this IP, your PC, 192.168.1.50. Default gateway, 192.168.11. Your friend's computer has this IP, friend PC, 192.16. At first, this looks confusing because both houses might use the same network, 192.24. But that is allowed because private IPv4 addresses are not routed over the public internet. Private IPv4 ranges include 1.0.08, 172.
Yeah, I know
These
that.
addresses are meant to be used privately inside homes and businesses. So your PC cannot directly send traffic to your friend's PC by saying 192.16,
So the idea of internal communication works with the router has two sides, the LAN side and the WAN side. Oh, okay. So how does internet communication work? Your router has two sides, the LAN side, private home network, and the WAN side, the public internet ISP network. So my PC, private IP, your router, LAN IP, that's my default gateway. Your router, public WAN IP. Your friend's router also has two sides. Where routing happens. When your PC wants to reach something outside of the network, it sends a packet to the default gateway. Yeah, okay. Your PC thinks this is the destination for my local network. No, send it here for the default gateway. The default gateway is usually your home router. When your router sends the packet to the ISP sends it through other routers eventually to get to the destination. Where's that come in? Okay, well, honestly, that's kind of a smart question. I didn't think about that, but I am curious. In most IPv4 networks, your router uses NATs. Well, usually they use PAT, but that's okay. Or network address translation. Your PC sends traffic like this: source IP, destination IP. Your router changes it to source IP, destination IP. So the internet does not see your private IP. It sees your router's public IP. So how's that work with VPNs then? Tell you the truth, I only ever have a VPN on my phone. I don't really ever turn it on my computer. Because I thought that was dumb. I thought that was just hiding me within my own local network. Maybe it is. I don't know. Okay. When the relay comes back, your router remembers when it sends the reply back to your PC. Real world. Okay, your PC, your friend's PC. Most of the time, your computer is not directly talking to each other by private. Instead, both of them are talking to both of you are talking to a game server. Okay, that makes sense because, playing games. Okay, your PC, your router, internet, game server, your PC, your friend, internet. So it's like the game server is kind of like the hub. Okay, that makes sense in like real life. Okay. Big CCNA takeaway. Your friend's router needs to say a rule called port forwarding. Without port forwarding, VPN or some other remote access setup, your friend's router will usually block unsolicited inbound traffic. Interesting. Okay, so here's the big takeaway. When two routers are directly connected like this, both interfaces are in the same subnet, but have different IP addresses. I guess that makes sense because my router in my house is not going to be directly connected to anybody else's router in anybody else's house. So therefore, it's gonna by default go through the ISP. Okay, your LAN, your router, your ISP routers. So could you say that my ISP is like a higher form of a default gateway, or that my ISP is kind of like a, what am I looking for the word? An enterprise? Did I spell that right? Hey, no, I did not. Oh, it's with an E. I'm sorry. I apologize. Okay. Is kind of like an enterprise with the ISP being the DHCP for the public side of my router in my house. Okay, let's let that think there for a second. Because the way I'm thinking of it, because like at a college campus, there's multiple server racks. They're all connected together, right? And they can all only have so many IP addresses, and then they delegate it out. And then they push it out to the real world if you need to get out, but everything's always going to stay in-house. So I'm thinking of the ISP as like the master that actually allows me to get to the world. Like if I didn't have an internet service provider, which obviously makes sense, they're a service provider for internet, then I have no way of getting outside of my local network. So does that mean that I could just have a LAN network and connect all my devices and have nothing ever talk to anything else? Like if I created my own network with my printer, my like I had multiple computers so that way they could all talk to each other and do whatever, and I could like file share whatever, but none of it was connected to the internet service provider, would it be protected from outside forces? Assuming that I don't have Wi-Fi. If I don't have Wi-Fi going on and everything's through the LAN, I would imagine that that would be like the most secure thing ever, because I'm not even tapped into the WAN. Now, I don't know what kind of benefit that would serve, but I'm just trying to, think about it.
Yes, that is a pretty good way to think about it, with one correction. Your ISP is not exactly a higher form of default gateway, but your ISP provides the next default gateway for your home router. So the chain looks like this. Your PC, home router, ISP router, more ISP internet routers, destination. Your PC's default gateway is your home router. Your home router's default gateway is usually an ISP router. And yes, your ISP often acts like the DHCP provider for the public WAN side of your home router. 2. Analogy.
That's crazy to think. Okay.
Think of your house like a small school. Inside the school, students ask the front office where to send things. Students equal to your devices.
Yes.
Front office equal to your home router. The front office handles anything inside the school. But if something needs to leave the school, the front office gives it to the district mail center. District mail center equal.
Okay, and okay. I can see it. It's just layers on top of layers. If we use the same school analogy, students are my devices. The teacher is the default gateway in the classroom. But in order to get things outside of the school, I need to go to the front office to have access to other classrooms or to have access to outside of the school. But I don't have to go to the front office to just go talk to the teacher who is across the hallway or even on the other side of the school. I can just go there. Okay, this is making a lot more sense. I'm sorry for this super huge detour, but I just had questions for why he put the IP address right here. But I think the reason why he did the IP address right here is that this is the network address. So that would mean that this is probably and that's why he has .1. So this is 192.168.13.1, and this is 192.168.13.3. Okay. All right. Sorry, I apologize for that, but I just was curious. I had to figure it out.
Okay, before looking at routes, let's configure the IP addresses. I'll just show the configurations on R1, since that's the router we'll be focusing on in this video. First, I configured its G00 interface with IP address 192.168.13.
And we got there through, we did enable, then we did config T interface, which you don't need the full interface. You could have just put int G0/0. Then he configured the IP address of IP address, and there's the IP. So here's the interface. We're right here. This, I was right. That is the IP address, which means that this is the subnet mask.
18.1, 255.255.255.0, and then enabled it with no shutdown.
Okay.
Then I configured G01's IP address.
Same
Notice
process.
that while I was still in interface config mode for G00, I used the interface G01 command directly, without returning to global config mode first. There is no...
Okay. This is my only complaint with this, the routers and stuff. I get that I'm in config interface. I understand that means IF. I just wish they would have added what interface I'm in. Like, and I really feel like that's a pretty easy, like, thing to do. Maybe it's not, because there's no way for me to know that I'm in this interface other than the fact that I'm the one who put it in and then I'm going down. But what if I'm in this interface and I'm doing a whole bunch of crap and then I got to get out of it and go to a different... I guess you could always just put that command in. It won't hurt anything to... If I'm already in interface G0/0 and then I say I want to go to that interface again, nothing's going to happen. You know, like it'll just be like, okay, you're in this interface.
No need to use exit to return to global config mode before entering interface G01. You can use the interface G01 command directly from interface config mode. I then configured G02 as well. To confirm, I used show IP interface brief, and you can see the IP addresses I just configured.
Okay, sometimes he says do show IP interface brief, and sometimes he just does show. And I don't know what the difference is between that.
Of course, I configured the other...
I don't care enough to go down another deep rabbit hole, but that's just a question I have.
...routers' IP addresses too, but for the sake of time, I won't show them here. As I said, in this video, we'll just focus on R1. Now let's take a look at R1's routing table. The command is show IP route. It displays the router's routing table. And here is the output. There are two main sections to the output. The codes at the...
Okay, I'm not going to lie. These codes, like, they elude me. They elude me.
...top and the actual routes at the bottom. The codes legend in the output of show IP route lists the different protocols which routers can use to learn routes, as well as the codes that represent them in the routing table. I've highlighted two in blue here. The first is L, which means local. This code is used for routes to the actual IP address configured on the router's interface, and these routes will have a /32 mask. If you look at the routes below, notice there are 3 routes with L that I've highlighted in blue, one for each of R1's interfaces. Then there is the C code, which means connected. These are routes to the network the interface is connected to, with the actual net mask configured on the interface. Notice there are also 3 routes with the C code in the output below. So even though we haven't configured any routes yet on R1, it already has 6 routes. When you configure an IP address on an interface and enable it with the no shutdown command, 2 routes per interface will automatically be added to the routing table, a connected route and a local route. Okay. Earlier, I mentioned that there are 2 main types of routing, dynamic routing and static routing. These connected and local routes, however, are neither. They are simply added automatically when an interface is configured. These are the routes we will focus on in this video. Okay, let me explain these routes in more detail. So I've highlighted 2 of the routes, one connected route to 192.168.1.0/24, and one local route to 192.168.1.1/32. So a connected route is a route to the network the interface is connected to. R1G02's IP is 192.168.1.1/24. What do the red and blue numbers mean here? Well, because it's a /24 address, the first 24 bits, the first 3 octets, are the network portion of the address. I've highlighted that portion in red. Then the last 8 bits, the last octet, is the host portion of the address, and I've highlighted it in blue.
Yep.
When you change that host portion to all zeros, the result is 192.168.1.0/24. And notice, that's the destination of that connected route. It's a route.
Now, he was able to just submit this, change this to 0 to find the network address because it was /24. If this would have been /25, it would not have been that easy. That's why we have this guy right here, which we will do later. All right.
Route to that network. So this provides a route to all hosts in that network. For example, 192.168.1.10.100.232, etc. Any address in that .0/24 range. Look back up at the routing table and notice that the route says 192.168.1.0/24 is directly connected, gigabit Ethernet 02. So R1 knows if I need to send a packet to any host in that network, I should send it out of G02. Okay, that's the connected route. Next, let's look at the...
Okay, so that means that because earlier he said he should have connected R1 to R4 and R3 to R2, so that way they were all connected, a full mesh network. So that would have been the fewest hops possible would have been R1 to R4 to the switch to the PC4. But now we have to make a choice between R3 and R2. Okay, but that means that if that was the case, then all of these routers need to be on the same network. If they weren't going to be on the same network, then we have to go through an ISP, or a lot of times they'll just call it like the internet, and they'll put a cloud. Okay, I think I'm understanding it.
The local route in more detail. A local route is a route to the exact IP address configured on the interface. A /32 netmask is used to specify the exact IP address of the interface. /32 means that all 32 bits are fixed. They can't change. So, even though R1's G02 is configured as 192.168.1.1/24, the local route is to .1/32, which specifies only that single address. It doesn't include 192.168.1.2, for example. So, with this route, R1 knows, if I receive a packet for this IP address, the message is for me. It's to my own IP address. Just to make things clearer, let me show it like this. /24 means that the netmask is 255.255.255.0. The first 24 bits of the netmask are all 1.
Because what we did is we added up the bits value. So So 192 means that we're using all of these. Actually, /24 tells us the value box that we're going to click. And the value box that we're going to click is going to be basically here all the way through, because this is 8. That's why it's called an octet. This is 8. That's why it's called an octet. And this is 8. That's why it's called an octet. And 8 plus 8 plus 8 is 24, which means that all of these are being taken up. So we add all of these numbers together, which creates not 225, 255. And that's why we have 0 here, because this is 24. So we're only adding up to 24. So that means that these are all free. Oh, I hope that makes sense.
So each octet is 255. These bits are fixed. They can't change. However, the last 8 bits, the last octet, are not fixed. They can be any number.
Yeah, they're free.
So the route for 192.168.1.0/24 matches 192.168.1.0 to 192.168.1.255. That means that if R1 receives a packet with a destination in that range, it will send the packet out of the G02 interface. Let's see some examples. A packet with a destination IP address of 192.168.1.2 is a match, because the IP address begins with 192.168.1. Because it's /24, the first 3 octets have to match. So R1 would send a packet out of G02.
So if you have the wrong IP address, if the device that you're using has the wrong IP address and it's sending it to the router won't know where to send it because it doesn't know what network it's in. Like, if this was my computer and I was sending it to my printer or something, I don't know, okay, it would match, and now it matches the network. The router knows it and is going to send it out of the G02 port, or interface rather. I need to stop saying port. Interface is the correct term. Okay. But if for some reason I have a bad IP address, or maybe I manually put the IP address in my computer, and this is 192.168.2.7, it would not match. And then the router wouldn't know where to send it because it doesn't know where it is. It doesn't know what its network is because it's outside the network. So then it would just sit still. And honestly, this probably makes a lot of sense. I bet this happens a lot of times, where because the computer would still say that it's connected to the internet. It would still say that it has connectivity, because in that IP address still looks good, but it's not in the network. It's not in the subnet.
.1.7 would also match this route, so R1 would forward the packet out of G02. Likewise, 192.168.1.89. A packet destined for 192.168.2.1, however, does not match. It cannot use this route, because the destination does not begin with 192.168.1. So what would R1 do with this packet? It would send the packet using a different route, or drop the packet if there is no matching route. The term match is very important, and I will use it a lot in this video and others. A route matches a packet's destination if the packet's destination IP address is part of the network specified in the route. Using an example on the right, 192.168.1.2 is part of the 1.0/24 network, so the route matches the destination IP. Destination 192.168.2.1 is not part of that network, so the route does not match that destination IP. Now, the local route to 192.168.1.1/32 is simpler. Because it's /32, all bits of the netmask are 1, so it's 255.255.255.255. All of these bits are fixed. They can't change. So, 192.168.1.1/32 matches only destination 192.168.1.1.
And that's because 8 times 4 is 32. 4, 8, 12, 16, 24, 28, 32. Right? Yes.
No other IP addresses. Okay, we looked at those connected and local routes that were automatically added to R1's routing table when we configured IP addresses on its interfaces. Now let's look at another fundamental concept, route selection. So R1 has a connected route to 192.168.1.0/24 and a local route to 1.1/32. Let's say R1 receives a packet and the destination IP is 192.168.1.1. Can you see the problem here? A packet destined for 1.1 is matched by both routes, 192.168.1.0/24 and .1/32. So which route will R1 use for a packet destined for 1.1? Will it send the packet out of G02, or will it receive the packet because the packet is for R1 itself? The answer is, it will choose the most specific matching route. So I explained what a matching route is. Let's see what most specific means. The route to 192.168.1.0/24 includes 256 different IP addresses, from 192.168.1.0 to .255. On the other hand, the route to 1.1/32 includes only one IP address, 192.168.1.1. It specifies just...
So is this a subnet inside the subnet?
one IP address, not 256 different IP addresses. So this route is more specific than the /24 route. So when R1 receives a packet destined for 192.168.1.1, it will select the route to 1.1/32. So R1 will receive the packet for itself rather than forward it out of G02. That's the purpose of local routes. They tell the router, keep the packet, don't forward it. This means R1 will de-encapsulate the packet and look at the contents inside, because the contents are addressed to R1 itself. So to summarize, the most specific matching route means the matching route with the longest prefix length. Both parts of that statement are important. The route must match the packet's destination, and it also must have the longest prefix length out of all the matching routes. That is the route that the router will use for the packet. Now let me point out these statements here in the output of show IP route on R1. You might have noticed them and wondered what exactly they mean. The top one says 192.168.1.0/24 is variably subnetted, 2 subnets, 2 masks. What exactly does that mean? Well, first of all, it's important to know that these 3 lines are not routes. They mean the following. The first line, 1.0/24 is variably subnetted, 2 subnets, 2 masks, means that in the routing table, there are 2 routes to subnets that fit within the 1.0/24 class A network with 2 different subnet masks, those being /24 and /32. The other 2 mean the same thing for their respective networks. To really understand these statements, you have to understand what a subnet is, but we haven't covered
Okay, I understand what a subnet is, but I don't understand why we have 2. Why do we have 1 IP address reserved? Because that's basically what /32 is doing. It's reserving this 1 IP address. But since it's a subnet inside of a subnet, no, it can't go out. It still can't go out at scope.
subnets yet in the course. We will cover subnetting soon in another video. For now, I just wanted to point out that these 3 lines are not routes, so you don't get confused by them. Generally, you can ignore this output in the routing table and just focus on the routes themselves.
So these are the routes themselves.
Now let's look at a few examples to practice route selection. R1 receives a packet destined for 192.168.1.1. Looking at its routing table, which route will it select for this packet?
Okay. 192.168.1.1. It's not gonna it's not gonna go to any of them, right?
And what will it do with the packet? If you want, you can pause the video now to think about the answer yourself.
It's either gonna drop.
So we have to find the most specific matching route in the routing table. This first packet is destined for 192.168.1.1, and when R1 checks its routing table, it will see that the most specific match is this one, to 192.168.1.1/32. It is a local route, so R1 will receive the packet for itself.
Oh, okay. I didn't realize that these are choices. I thought it was asking which interface it was going to go out of. I was still right, though.
Note that this packet matches two routes in the routing table, the route for 1.0/24 and the route for .1/32. But the /32 route is more specific, so it will be selected. Here's another example. Packet 2 has a destination IP address of 192.168.13.3. Which route will R1 select for this packet? And what will it do with the packet? The most specific matching route, actually the only matching route for this packet, is this connected route to 13.0/24. So R1 will send the packet to the destination, which is connected to the G00 interface. Here's a third packet, destination IP 192.168.1.244. What will R1 do with this packet? The only matching route is this one to 1.0/24, so R1 will use this route to forward the packet. It's a connected route, so R1 will send the packet to the destination, which should be connected to that interface. And here's a fourth packet, destined for 192.168.12.1. What will R1 do with this packet? There are two matching routes, but the most specific one is this local route for 192.168.12.1/32. So R1 will receive the packet for itself. Okay, let's do one more practice question. Packet 5 is destined for 192.168.4.10. What will R1 do with this one? Because there are no matching routes in the routing table, R1 will have to drop this packet. Unlike switches, which flood frames if they don't know where the destination is, routers do not. Routers never flood packets. If the router doesn't have a route to the packet's destination, it will drop the packet. Okay, now let's try to review everything in this video in one slide. This will be just a wall of text, but hopefully it will help you review what we learned in this video.
Let's do it.
Routers store information about destinations they know in their routing table.
Okay.
It's like a switch's MAC address table, but of course it functions differently. And when they receive packets, they look in the routing table to find the best route to forward the packet. Each route in the routing table is an instruction. A route says, to reach destinations in network X, send the packet to next hop Y, which is the next router in the path to the destination. Now, on most routers, they will have lots of routes like this. To reach destination X, send packets to next hop Y. However, in this video, we didn't actually look at this kind of route. We looked at connected and local routes. Connected routes say, if the destination is directly connected to this router, send the packet directly to the destination. Or if the destination is your own IP address, receive the packet for yourself. This is how a local route works. Anyway, the point is that the routing table is a set of instructions for the router, telling it how to forward packets. In the next video, we will look at how next hops work when we learn about static routes. When you configure an IP address on an interface and enable the interface, two routes are automatically added to the routing table. The first is a connected route, indicated with code C in the routing table. It is a route to the network connected to the interface. For example, if the interface's IP is 192.168.1.1/24, the connected route will be to 1.0/24. I'm repeating the point above, but it tells the router to send a packet to a destination in this network, send it out of the interface specified in the route. Then, the other kind of route is a local route, indicated by code L in the routing table. It's a route to the exact IP address configured on the interface. So, if the interface's IP is 192.168.1.1/24, the route will be to 1.1/32. A /32 net mask is used to specify just the one IP address. This tells the router, packets to this destination are for you, and you should receive them for yourself, not forward them. Okay, we also talked about how routes match destinations. A route matches a destination if the packet's destination IP address is part of the network specified in the route. For example, a packet to 192.168.1.60 is matched by a route to 1.0/24, but not by a route to 0.0/24. Now, if a router receives a packet and it doesn't have a route that matches the packet's destination, it will drop the packet. This is different than switches, which flood frames if they don't have a MAC table entry for the destination. Final point. If a router receives a packet and it has multiple routes that match the packet's destination, it will use the most specific matching route to forward the packet. And the most specific matching route means the matching route with the longest prefix length. This is different than switches, which look for an exact match in the MAC address table to forward frames. The frame's destination MAC address must be the exact same as the entry in the MAC address table. There's no concept of most specific match in switches. Okay, so that was a summary of this video. Hopefully it helps you review what you learned in this video, because this is important fundamental information. And here are the general topics we covered in this video. I introduced the concept of routing, the process routers use to determine the path that IP packets should take over a network. We examined the routing table on a Cisco router, specifically looking at connected and local routes, which are automatically added to the routing table when you
Man, he explained all of this so well. Oh my gosh, he explained it so well.
Figure an IP address on an interface. And we also looked at routing fundamentals, how routers select which route to use to forward a particular packet. They do that by looking for the most specific matching route in the routing table. Now, there's still lots more to cover about routing, and in the next video, we'll dig deeper into the topic by looking at static routes. Okay, now let's move on to the quiz to test your understanding of the concepts we covered in this video. Here's quiz question 1. The IP address configured on a router interface will appear in the routing table as what kind of route? Pause the video now to select the best answer.
The IP address configured on a route interface will appear in the routing table as what kind? Is connected?
Okay, the answer is C, local. When you configure an IP address on an interface, 2 routes are automatically added to the router's routing table, assuming the interface is enabled. Note that if the interface is shut down, the routes won't appear. Anyway.
Still don't understand why we have these two and why we have a /32. I know that that wasn't the point of this video. But I'm just, yeah.
The routes that are automatically added are a connected route to the network and a local route to the exact IP address configured on the...
Okay, this is the connected and this is the local route. The local route must be very, have some type of significance. I just don't know what it is yet.
The router interface. Okay, let's go to question 2. Examine R1's routing table. What will it do when it receives a packet destined for 192.168.3.25?
Okay, .3.25. We don't have a .3 at all. Well, yeah, we do. How is that 13 and this is 3? That makes sense. This doesn't make sense. This is going to be sent to the local.
Pause the video now to examine R1's routing table and select the best answer.
It could drop the packet, but it's probably going to receive the packet.
Okay, the answer is B. It will receive the packet for itself.
Yeah.
R1 has this local route to 192.168.3.25/32. Which
okay,
means that
but
this IP...
I don't understand how we went from 192.168.13.0/24, which means that these bits in 13 are supposed to be frozen, but yet we're directly connected to 0.3.0/24. That doesn't make any sense. These bits are supposed to be frozen, but very clearly they're not. These bits are frozen. These bits are frozen.
IP address is configured on its G02 interface. So, packets destined for 3.25 are destined for R1 itself. Okay, let's go to question 3. Which of the following statements about the behavior of routers and switches are true? Select 2. Pause the video now to select the best answers.
Routers do not flood packets. Switches do flood packets with an unknown destination. Routers drop packets with an unknown destination. Switches drop frames of an unknown destination. It's either B or C. So switches do flood, but they don't flood frames. I think the answer is C. Oh, select 2. Then it's A.
Okay, the answers are B and C.
Yeah.
Switches flood frames with an unknown destination. Okay. Those are called unknown unicast frames. Routers, on the other hand, never flood packets. Instead of flooding packets with unknown destinations, the router simply drops them. Okay, let's go to question 4. Which 2 types of routes are automatically added to the routing table when you configure an IP address on an interface and enable it? Pause the video now to select the best answer.
Which 2 types of routes are automatically added to the routing table when you configure an IP? So it's going to be, I think it's C and L. I know it's L. Local is the /32.
Okay, the answer is A, C and L. As shown in the show IP route output on the right, C stands for connected and L stands for local. These 2 routes are added when you configure an IP address on an interface and enable it. Okay, let's go to question 5. Examine R1's routing table below. If R1 receives a packet destined for 10.0.1.23, how many routes match that destination? And which...
It's going to be this one. 0.0, 0.1, 0.23. It could be either C or L, but L is the most is more correct. So the 1 match, 2 match routes, most specific. Yep.
Which is the most specific matching route?
C.
Pause the video now to examine the routing table and select the best answer.
C.
Okay, the answer is C.
Woo!
There are 2 matching routes, 10.0.1.0/24 and .23/32. And the most specific matching route is the route to .23/32, so that route will be selected. It's a local route, so that means R1 will receive the packet for itself. It won't forward it to another device. Okay, that's all for the quiz and this video. I hope it was helpful. Thanks for watching.
Yeah,
Before finishing this video, let me thank my JCNP level channel members. To become a member, please click the join button under the video. Thanks to Jonathan Makara, Velvet Jacob, George Streeter, Funny Dart, Nasir
These are the
Chowdhury,
real
Devin
MVPs
Suku,
right
Gustavo
here,
Villar,
guys.
Gerard Baker, Marcel Lord, Pavel M, Mr. Erlison, Dragos Hernea, Zakib Shah, Mayor Salman, Mason Anderson, Vithouse194, Gina Lindley, Nahimia, Justin Watke, Mark Jackson, Bold 1C1U, Michael Carroll, Gerald Guillaume, Gabriel Braga, Renan Marias, Hector
This is
Hernandez,
also 3
Ali
years ago,
Polat,
too.
Maratuba, Roji Kuriakos, Arpad Konives, 5 Feet, Daniel Brown, Tricky Mickey 123456, Scott Thompson, Jose Alvarez, Kevin Hayes, Hussein Yabus, Samuel Tavares, Mustafa Irsoy, Dear Diso, Nasser Zahar, Alexandru Badic, Brian Grant, Georgi Gemejev, Ahmed Ismail, Dibya Swain, Arlen Plagaria, Adelson Pereira, Abdo Zizo, Farad69, and Lucian Stoichitoyu. Sorry if I pronounced your name incorrectly, but thank you so much for your support. Thanks to you and...
All right. Good. Next one. I think the next one is going to talk about statics. This is part 2. But I really want to do the packet tracer for part 1.
Welcome to Jeremy's IT.
This is not for part 1. This is just a packet tracer for all of it. And this is troubleshooting. Okay. We're going to back up. I guess we are going to do part 2. Yeah. Okay. I am going to go grab some tea. And I'm going to go grab some cookies because, like, that's the breakfast of champions. And I'll be right back. Here's the music in case you guys were curious what it was. There you go. Be right back. All right. I'm back. I got some tea. And I found some crackers. I'm ready to take on the world. All right, let's put this back down. 37 minutes, dude.
Welcome to Jeremy's IT Lab. This is a complete course for the CCNA, Cisco Certified Network Associate exam. In this video, we will cover static routing, a very important topic to understand for the CCNA exam. In the previous video, we looked at the basics of routing, how routers decide where to forward packets. And we looked at two types of routes, local routes and connected routes. Those routes are automatically added to a router's routing table when you configure an IP address on an interface. Local routes provide a route to the router's own IP address, and connected routes provide a route to the network the interface is connected to. However, if you want the router to be able to send traffic to destinations that aren't directly connected to the router itself, local and connected routes aren't enough. Today's topic, static routes, enable routers to send packets to remote destinations that aren't directly connected.
That's what we watched just in a second.
Here's what we'll cover in this video. First, we'll briefly review connected and local routes, while looking at the rest of the network topology I introduced in the last video. Then I will introduce static routes, and how we can use them to instruct routers about how to forward packets. And of course, we'll see how to configure static routes in the CLI of Cisco routers. Unlike connected and local routes, static routes are not automatically added to the routing table, and must be manually configured. Finally, I will also explain the concept of default routes.
I think you can also push out static routes. Like a massive update. I'm not entirely certain about that. But that sounds like something that has been automated. Like, I don't know. Well, I guess we'll find out.
Connected and local routes by configuring IP addresses on the routers and checking their routing table. In the last video, I showed R1. So for this video, let's start from R2. I configured IP addresses on G00 and G01 and enabled both interfaces. Remember, if an interface is disabled, the connected and local routes for that interface will...
I'm starting to be able to follow these commands.
The routing table. Now, before I show the routing table, I want you to think about what routes there will be in the routing table. There should be one connected route and one local route per interface, so a total of 4 routes. Remember, these routes are added automatically when you configure IP addresses on router interfaces. So what will the destination of each route be? Well, the connected routes are routes to the networks R2's interfaces are connected to. So there should be one.
Okay, I'm starting to understand. The connected is the route the interface is connected to. So this is the route. Or sorry, this is the C. This is the connected. And then the local is the IP address that's configured on the interface. That's why it reroutes it back to itself. Okay.
One route to 192.168.12.0/24 and one route to 24.0/24. And then the local routes are to the exact IP addresses configured on R2's interfaces. So there should be a route to 192.168.12.2/32 and a route to 24.2/32. Okay, here are the routes. Note that for the sake of space, I'm not showing all of the different codes listed at the top of the arrow. Remember, C means connected and L means local. Anyway, as expected, R2 has 2 connected routes, one to 12.0/24 and one to 24.0/24. Also, it has 2 local routes, one to 12.2/32 and one to 24.2/32. So to summarize, R2 knows how to reach its own IP addresses and destinations in its connected networks. But it doesn't know how to reach
That makes
destinations
sense.
in remote networks. By remote networks, I mean networks not directly connected to R2. So R2 knows how to reach destinations in 192.168.12.0/24 and 24.0/24 networks, including its own IP addresses in those networks. But it doesn't know how to reach any of the other networks in the topology. If R2 receives packets destined for hosts in these other networks, it will have to route. R2 doesn't know where it should send them. And here's R3's configurations. 192.168.13.3/24 on its G00 interface, and 34.3/24 on G01.
Okay.
So which routes will it have in its routing table? As you should know by now, it has 2 connected and 2 local routes. So let on R2,
So okay.
R3 knows how to reach its own IP addresses. Those are the local routes, and destinations in its connected networks. Those are the connected routes. But it doesn't know how to reach destinations in remote networks. So it knows how to reach 192.168.13.0/24, including its own IP of 13.3/.
Dang it. I'm so sorry. Y'all should be able to hear it now.
And it also knows 34.0/24, including its own IP of 34.3/32.
I apologize.
It doesn't know how to reach any of the other networks, though. So, for example, if it receives a packet and the destination is PC4's IP address, 192.168.4.10, R3 wouldn't be able to forward the packet. It would have to drop it. And here's R4's configurations. Note that R4 has 3 interfaces in use. So how many routes will it have in its routing table? The answer is 6, 3 connected and 3 local. Same as R2, R3, and also R1, which we looked at in the previous video. R4 knows how to reach its own IP addresses and destinations in its connected networks, but not how to reach destinations in remote networks. These are the networks it knows, and these are the ones it doesn't. For example, if it receives a packet destined for PC4, 192.168.4.10, it has a route to 4.0/24, so it would be able to forward the packet to PC4. However, if it receives a packet destined for PC1, 192.168.1.10, it doesn't have any routes that match that destination IP, so it would have to drop the packet. So, all of these routers have connected and local routes. Now let's start looking at how we can configure them to allow PC1 and PC4 to communicate.
Okay.
Notice that I've colored the interface labels for each device, and also added interface names for PC1 and PC4.
Okay, look, I know. Look, you can call it gay if you want, but like color coordinating shit like helps me so much. Now, I wish that the color coordination was happening between G1 and G's. Like, I wish that these were the same. Maybe there's a reason why they're not.
PC1 and PC4 are Linux hosts, and their default interface name is ETH0, Ethernet 0. These colors will make things easier to understand as
the way Linux like labels their stuff makes so much more sense. Like, it just does.
Demonstrate how packets move through the network. So first we are going to look at the concept of default gateway. End hosts like PC1 and PC4 can send packets directly to destinations in their connected network. PC1 is connected to 192.168.1.0/24, so it can directly communicate with other hosts in that network. And PC4 is connected to 4.0/24, so it can directly communicate with hosts in that network. However, to send packets to destinations outside of their local network, they must send packets to their default gateway. Gateway is an old term for router, so it means default router. So these are the configs on PC1 and PC4.
Okay. ETH0, that's their Ethernet port. This is their address. Yes, this is the default gateway. Okay, which is going to be this right here. So then that means 0.4. Why isn't it not 1? Interesting. Oh, because he was trying to make it match R4 for organizational purposes.
In Linux, the interface configurations are stored in a text file that you can edit. On PC1, for example, there is the line address 192.168.1.10/24, which configures the IP address as 1.10 with a prefix length of /24. And below that is the default gateway configuration, gateway 192.168.1.1. So to send packets to destinations outside of its local network, PC1 will send packets to R1. The default gateway configuration is also called a default route. Basically, it's a route to O.O.O.O/O. All netmask bits are set to 0. None of the bits in the address are fixed. O.O.O.O/O includes all addresses from O.O.O.O to 255.255.255.255. It's a route that includes everything. Remember the concept of most specific matching route in the previous video? Well, the default route is the least specific route possible because it includes all IP addresses. O.O.O.O/O includes over 4 billion IP addresses. On the other hand, a /32 route, like a local route, is the most specific route possible.
It's crazy that 4 billion sounds like a lot, when in reality, like, that is absolutely nothing in terms of, like, IP addresses. Like, that's insane. That there's roughly 4.2 billion IP addresses in IPv4, and I think that it's like 10 times that in IPv6,
because it specifies only one IP address. For example, 192.168.1.1/32 specifies only one IP address. So the default route says, if there aren't any more specific matches for this packet, don't drop it, send it via this route instead. Later, we'll see how to configure a default route on a Cisco router and what it can be used for. But for now, just understand how it works for end hosts like PC1 and PC4. End hosts usually have no need for any more specific routes. They just need to know, to send packets outside of my local network, I should send them to my default gateway. So if PC1 wants to send a packet to PC4, the source IP address in the IP header is 192.168.1.10, PC1's IP, and the destination IP is 4.10, PC4's IP. Now here's a major point. What will the source and destination MAC addresses be in the Ethernet header? This is where you can start to really understand the role of layer 2 and layer 3. At layer 3, PC1 wants to send the packet to PC4, so the destination is PC4's IP, 192.168.4.10. However, it has to first forward this packet to its default gateway, R1. So it will encapsulate the packet in a frame, and the destination MAC will be R1G02's MAC address. Now, how does it know R1G02's MAC address? To learn it, PC1 will first send an ARP request to 192.168.1.1, R1G02's IP address. I will show this part of the process in more detail in the next part of the course, called Life of a Packet. To keep things a bit simpler in this video, let's just assume each device already knows its neighbor's MAC addresses. I won't show all of the ARP exchanges. So, PC1 sent that frame to its default gateway, R1.
Bro, this is insane. Like, all of this happens in a split of a second to, like, just do everyday life. Man, there's a bug in here. To do, like, everyday life. That's crazy. That's crazy that, like, all of this shit is happening like that. In every single, like, this moment right now, getting the packets for this video, the packets for this stream, like, that just blows my mind.
R1 receives the frame, it will de-encapsulate it, meaning it will remove the layer 2 header and trailer, and look at the inside packet. It will then check the routing table for the most specific matching route. It has to make a decision about what it will do with this packet. So here is R1's routing table at the moment, just connected and local routes. Do any of these routes match the destination IP of the packet? No, R1 has no matching routes in its routing table. So what will it do with the packet? It has no choice but to drop it. In its current state, R1 doesn't know how to properly forward the packet. To forward it, R1 needs a route to the destination network, 192.168.4.0/24. Remember, routes are instructions. R1 needs a route to say, to send a packet to destinations in network 192.168.4.0/24, forward the packet to next hop Y. Now we know the destination, the 4.0/24 network, but what should be the next hop? What is the next router in the path to the destination? Actually, there are two possible paths that packets from PC1 to PC4 can take. One is the path via R3, PC1 to R1 to R3 to R4 to PC4. The other path is the one via R2, PC1 to R1
I
to
talked
R2
about this before. There isn't a shortest path. They're both identical because whether a path is short or not is determined by how many hops it has to go. So if we did have a line that went from here, from R1 to R4, that would be the shortest path because we got rid of a hop.
To R4 to PC4. In this video, we will use the path via R3, not the path via R2. So we won't actually use R2 much in this video.
And there's no reason why he chose that. He just chose. He could have very easily have picked R2. He just, for whatever reason, picked R3. It doesn't really matter.
The reason I included R2 in the diagram is that I wanted to demonstrate that if there are multiple paths to the destination, you can choose which one the router should use. Now, it is possible to configure the routers to use these multiple paths differently. Instead of choosing one path, they can load balance between path 1 and 2. That means some packets will take path 1 and some will take path 2. Or they could, for example, use path 1 as the main path and path 2 as a backup path. You will learn about these techniques later in the course. In this video, we will only use path 1.
Because the goal of the packet is to make its destination. So if it can't go this way, it's going to go around and go a different direction. That's why, like, if you've ever been given if someone's ever emailed you, this has happened to me before with, like, certain like service providers, not just internet service providers, but like setting up internet or setting up electricity or security or anything like that in a new house or a new apartment. They'll probably send you an email confirmation, and it might take a little bit for you to receive that email confirmation, not as fast as you're used to receiving it, because it's sending out all the ARP requests, it's sending out all the IP, like it's doing all the things, and it's trying to find the fastest way to you.
Via R3. Now, to ensure PC1 and PC4 can communicate with each other, it's not just R1 that needs another route. Each router in the path needs two routes. A route to 192.168.1.0/24, PC1's network, and a route to 4.0/24, PC4's network. This ensures two-way reachability, which means that PC1 can send packets to PC4, and PC4 can send packets to PC1. If, for example, all routers had routes to 192.168.4.0/24, but not 1.0/24, PC1 would be able to send packets to PC4, but PC4's replies wouldn't be able to reach PC1. R4 would drop the reply, because it would have no route that matches destination 192.168.1.10. So, we want two-way reachability. It's worth noting that routers don't need routes to all networks in the path to the destination. For example, R1 doesn't need a route to 192.168.34.0/24. It just needs to know, to send packets to 4.0/24, I should send the packets to R3. R3 will take care of the packets after that. And likewise, R4 doesn't need a route to 192.168.13.0/24. R4 just needs to know, to send packets to 1.0/24, I should send the packets to R3. R3 will take care of the packets after that. Okay.
Yeah. So basically, each hop is only responsible for doing the next hop. So this switch, if PC1 is trying to reach to PC4, its job is to just send it to the switch. Then the job switch is to figure out how to get there. Oh, it needs to go to the default gateway. So then it goes to R1. R1's goal is to not get it to here. I mean, it ultimately is, but its goal is to just get it to the next hop. The next hop is going to be R3 or R2. In this case, is we picked R3. And then so forth and so forth. So on and so on.
Okay, continuing on. R1 already has a connected route to 1.0/24, and R4 already has a connected route to 4.0/24. However, the other routes must be manually configured using static routes. Before we get into actually configuring static routes, let's plan out the routes we will configure. Here's a chart of the routes R1, R3, and R4 need to allow PC1 and PC4 to communicate with each other.
See, there's the next hop.
In blue are R.
So here's R1. We're right here. Interesting. That's our destination. Okay.
1 and R4's connected routes. Note I listed the next hop as connected. Then in red are the static routes we have to configure. I will show the answers, but before that, I want you to pause the video and think about what the next hop IP address should be for each route. Now let's check. For R1 to send a packet to the 4.0/24 network, what is the correct next hop IP address?
Okay. The next hop should be 192.168. .1. Yeah, right?
Remember, we're using the path via R3 for this video, not the path via R2. The answer is...
Okay, so this I don't understand where he's getting this 13 from. That's what I don't understand. Because nowhere in... Okay, no, here it is. This is where we're getting the 13 from. Never mind. I retract my statement. So we just put connected. So the next hop's here. Then the next hop is going to be 34.1. No, 0.4. Because this was 13.0. That's the network. And then 13.3 is here. So then the next hop's going to be 192.168.34.4.
192.168.13.3, the IP address of R3's G00 interface. R1 has a connected route to 192.168.13.0/24, so it knows how to reach 13.3. It can then use that IP address as a next hop to send packets toward the 4.0/24 network. Okay, next one. What next hop IP should R3 use to send packets to the 192.168.1.0/24 network?
34.4.
The answer is 192.168.13.1. R1.
Why? Because it's the default?
G00 interface. And how about 4.0/24? It should send packets to 192.168.34.4, R4's G01 interface. Finally, what next hop should R4 use to send packets to the 1.0/24 network? The answer.
So R1 sent it to this, which is right here. See, this is what I'm saying. Like, I wish the colors coordinated with each other. So went to here. And then it sent it to its default gateway. It sent it back to itself? Question mark. And then it sent it to here. So is the next one going to be 192.168.34.1?
The answer is 192.168.34.3, the IP address of R3's G01 interface.
Now that doesn't make any sense to me. Where did he get 0.3 from?
Okay, we've planned the static routes we need to configure. To allow PC1 and PC4 to communicate with each other over the network, let's configure these static routes on R1, R3, and R4. First up, let's configure R1's route to 192.168.4.0/24. Here is the format of the command. From global config mode, IP route, followed by the destination network IP, netmask, and next hop IP. So for R1's route to the 4.0/24 network, the command is this: IP route 192.168.4.0, 255.255.255.0, 192.168.13.3. That's it. Fairly simple. I then checked R1's routing table. Notice I highlighted...
Okay. We are configuring IP route, IP address, netmask, next hop. So this is the IP address. I'm just not understanding certain IP addresses. Like, why did we use 0.4 right here?
The code for static routes. It's S, as you might have guessed. And I've also highlighted the route itself in the table. Notice in square brackets there are two numbers, 1/0. What do those numbers mean? They are the route's administrative distance and metric. We will cover these concepts later in the course. Don't worry about their meaning for now. I'm just pointing them out in case you're curious what those numbers are. Okay, that's all we have to configure on R1. It now knows that, to reach PC4's network, it should forward packets to 192.168.13.3.
Okay, I gotta understand this. It's always better to number.
G01 interface. Okay.
I do not understand how we figured out the next hop. Okay, so what exactly am I confused about? Let's see if we can pin it down. So what I don't understand is why we did 13 point, well, is 13.3 because it's in router, is it because it's in R3? And then why did it go to 13.1? Is the reason we did 13.3 because that is the IP address of R3 G0/0, and if that is the case, then how and why did the next hop be, that's poor grammar, next hop, why was the next hop 13.1? Is that because it sent the packet to itself so that it could push it out? Question mark. 2. So then I don't understand. Oh, you guys can't see this. It's just I'm just looking at the image, that's all. Okay. So then the 34.4 think I understand the 34.4 because that should be the IP address of the R4. But then how did we get 34.3? I thought that every gig interface had to be on its own IP address. Okay, so then the other thing is the IP route. How is the IP route 0.4.0? So 192.168.4.0. How is the IP? Damn it. Yeah, how is that possible if the network that it's on is 0.1.0/24? 0.1.0/24. Shouldn't the third octet be frozen? And be the only one to move? Yeah, because shouldn't the IP route be well, okay, so and its next hop is R3. Okay, we're gonna let that cook. Okay, we're gonna go back and we're gonna listen to this again.
Now, to ensure PC1 and PC4 can communicate with each other, it's not just R1 that needs another route. Each router in the path needs two routes, a route to 192.168.1.0/24, PC1's network, and a route to 4.0/24, PC4's network. This ensures two-way reachability, which means that PC1 can send packets to PC4, and PC4 can send packets to PC1. If, for example, all routers had routes to 192.168.4.0/24, but not 1.0/24, PC1 would be able to send packets to PC4, but PC4's replies wouldn't be able to reach PC1. R4 would drop the reply, because it would have no route that matches destination 192.168.1.10. So, we want two-way reachability. It's worth noting that routers don't need routes to all networks in the path to the destination. For example, R1 doesn't need a route to 192.168.34.0/24. It just needs to know, to send packets to 4.0/24, I should send the packets to R3. R3 will take care of the packets after that. And likewise, R4 doesn't need a route to 192.168.13.0/24. R4 just needs to know, to send packets to 1.0/24, I should send the packets to R3. R3 will take care of the packets after that. Okay, continuing on. R1 already has a connected route to 1.0/24, and R4 already has a connected route to 4.0/24. However, the other routes must be manually configured using static routes. Before we get into actually configuring static routes...
Okay, so R1 is already connected to this. And R4 is already connected to this.
Let's plan out the routes we will configure. Here's a chart of the routes R1, R3, and R4 need to allow PC1 and PC4 to communicate with each other. In blue are R1 and R4's connected routes. Note I listed the next hop as connected. Then in red are the static routes we have to configure. I will show the answers, but before that, I want you to pause the video and think about what the next hop IP address should be for each route. Now let's check. For R1 to send a packet to the 4.0/24 network, what is the correct next hop IP address? Remember, we're using the path via R3 for this video, not the path via R2. The answer is 192.168.13.3. The IP...
So this is the destination. It's connected, so we don't need to worry about it because it's actually connected to it. So then it goes here, and then it goes here. Okay, hold on.
Remember, we're using the path via R3 for this video, not the path via R2. The answer is 192.168.13.3, the IP address of R3's G00 interface. R1 has a connected route to 192.168.13.0/24, so it knows how to reach 13.3. It can then use that IP address as a next hop to send packets toward the 4.0/24 network. Okay, next one. What next hop IP should R3 use to send packets to the 192.168.1.0/24 network? The answer is 192.168.13.1, R1's G00 interface. And how about 4.0/24?
Oh, is it because it has to go back? No. All right, what do we got?
You are mixing up 3 different things, and that is why this feels confusing. Destination network equal to the network you want to reach. Next hop IP equal to the neighboring router interface you send the packet to next. Interface IP equal to the IP address assigned to a specific router port. For this command on R01, IP route 192.168.4.525.525. IP route 192.1, if you need to reach the network. R1, if you need to reach the network 192.1. Send the packet.
I hate when it glitches out. If R1, if you need to reach the network 192.168.4.0/24, send the packet to R3 at 192.168.13.3. The destination is this. The next hop is this. Those are not supposed to be the same network. Okay, I understand that, but nowhere... I understand that 13.3 is inside the network of 13.0/24. What I don't understand is that 13.3 is not labeled anywhere on here. So why is it going there? Why is that the next? Okay, no, point 3 is here. Point 1. Okay, so because that's the next hop. Okay, those are not supported by the same thing. Analogy. Let's see if it's gonna glitch out again.
Think of routing like giving directions. You are at your house and want to get to your friend's house. You do not say, "To get to my friend's house, first drive to my friend's house." That would not help. Instead, you say, "To get to my friend's house, first turn onto Highway 13." In routing, destination equal to friend's house. Next hop equal to the next road intersection you should take. So when R1 says, to reach 192.1 says, to reach 19/24.
Okay, so to reach this, our destination, we need to go here. To reach this, we need to go there. And this is what I don't understand. Okay, I'm understanding it more. But where do we get the 13.1? I understand that 13.1 is a part of this network. But is that 13. Oh, shit. So is this 192.168.13.1 and this is 192.168.13.3? I just assumed this entire router was using this, but that doesn't make any sense. These two interfaces have to be on the same subnet. They have to be part of the same network. The router takes care of where it needs to route to. So each interface is on a different Okay, hold on. Network. So for example, R1G slash is on the, what is it? The 168.1.0 network, or the 1.0 network. And that is on the 13.1. No, okay, hold on. I gotta make sure my shit makes sense. Okay, I think that I understand. Is it that the interface is on a different network? For example, the RG00. No, it's 02. 02 is on the 1.0 network, and the 00 is on 13.0 network. That's not how you spell it necessarily. Okay. Not the whole router itself necessarily. All right, we're gonna finish reading this while that's cooking. Okay. More in-depth. PC1, R1, R3, R4. So the LAN goes here. R3, that the link is this. R3 to R4, the link is that. PC4 is this. Each link / network has its own subnet. Yes, so exactly what I just said is true. R1 interface. Yes. So what I just was trying to explain is correct. Now the question is did I explain it correctly? R1 already knows about direct connection networks, so R1 directly knows, or already knows. Is sending to the packet to itself. No, that route is not for R1. That route is for R3. R3 has this route. Destination is this, and then the next hop is 13.1. Okay. Yes, you've got it. The route as a whole is not on one network. Instead, each router interface belongs to a network. This makes sense now. So This is our destination. We're already connected. This is our destination. So we want to go here. We're over here. That means our next hop, where we have to go to first, is 192.168.13.3. So that means here. Now our destination is now this, because we want two-way communication. So that means our next hop is going to be 13.1, which is going to be here. So then now our next destination is back to the PC4. So we want to go from here to 34.3, and then that's going to go to 34.4.
It should send packets to 192.168.34.4, R4's G01 interface. Finally, what next hop should R4 use to send packets to the 1.0/24 network? The answer is 192.168.34.3, the IP address of R3's G01 interface.
Okay, because the interface is here and that's there. So each interface has its own IP address, and each interface has to be on the same network as the interface that it's connected to. Has to be on the same network. Okay. Man, that took a lot of brain power, but I think I understand it all. Sorry.
Interface.
But I had to understand that.
Okay, we've planned the static routes we need to configure. To allow PC1 and PC4 to communicate with each other over the network, let's configure these static routes on R1, R3, and R4. First up, let's configure R1's route to 192.168.4.0/24. Here is the format of the command. From global config mode, IP route, followed by the destination network IP, netmask, and next hop IP. So for R1's route to the 4.0/24 network, the command is this: IP route 192.168.4.0, 255.255.255.0, 192.168.13.3. That's it.
Okay, so R1 is trying to route to this. Dude, I get like 10 spam calls a day. It's insane. Okay. R1 is trying to get to this. So this is our route. This is our subnet mask. And then this is our next hop. Our next hop is going to be over here. Okay.
That's it. Fairly simple. I then checked R1's routing table. Notice I highlighted the code for static routes. It's S, as you might have guessed. And I've also highlighted the route itself in the table. Notice in square brackets there are two numbers, 1/0. What do those numbers mean? They are the route's administrative distance and metric. We will cover these concepts later in the course. Don't worry about their meaning for now. I'm just pointing them out in case you're curious what those numbers are. Okay, that's all we have to configure on R1. It now knows that, to reach PC4's network, it should forward packets to 192.168.13.3, R3. Next up, R3. It needs two routes. 1 to...
So it's going to say that its routes, because it needs to be able to go back, right? So its route's going to be 13.1. The net mask is going to be 0.0. And then the next hop will be 34.4.
1.0/24 and 1 to 4.0/24. The format of the command is the same as on R1. If you can, pause the video and try to figure out the correct commands on R3. Here is the route to the 192.168.1.0/24 network, with R1 as the next hop. And here is the route to 4.0/24 with...
Okay. So our destination here. So that means our next hop is going to be here. But if our destination is over here, the 4.0, then our next hop is going to be 34.4. Okay.
R4 as the next hop. And then I checked R3's routing table too. Again, you can see both routes there with their next hop IP addresses. To reach 192.168.1.0/24, send packets to R1. To reach 4.0/24, send packets to R4. And finally, let's configure R4's route to the 192.168.1.0/24 network. Again, try to pause the video and figure out the...
So then our destination is going to be 0.1.0, because that's PC1. And then our next hop is going to be 34.3. I think
Correct
I understand
command if you
it.
can. Here is the answer. IP route 192.168.1.0, 255.255.255.0, 192.168.34.3, using R3's G01 interface IP address as the next hop. And here is R4's routing table now. So, we have now configured all of the static routes necessary for PC1 and PC4 to communicate. Let's test it out and see if they can actually communicate with each other. To test it out, I pinged from PC1 to PC4, and the ping was successful. As I've highlighted, it says 5 packets transmitted, 5 packets received, 0% packet loss. If the ping is successful, that means there is two-way reachability. PC1 can reach PC4, and PC4 can reach PC1. If PC1 could reach PC4, but PC4 couldn't send replies back to PC1, the ping wouldn't work. So the configurations were successful. Now, let me briefly show how a packet from PC1 to PC4 is encapsulated, de-encapsulated, and re-encapsulated in different frames as it travels through the network. We will examine this process step by step in the Life of a Packet video coming up soon, but this is just a preview. You don't have to think too much about the process yet. As you saw earlier, when PC1 sends a message to PC4, the layer 3 destination is PC4's IP address, 192.168.4.10. However, at layer 2, the destination is PC1's default gateway, which is R1's G02 interface. Now R1 has the packet, and it's R1's job to forward it to the next hop, R3. To do so, it encapsulates the packet in a new Ethernet frame. This time, the destination of the frame is the next hop's MAC address, so the MAC of R3's G00 interface. Now R3 has the packet and must forward it to the next hop, R4. To do that, it once again encapsulates the packet in a new Ethernet frame, and the destination of that frame is the MAC of R4's G01 interface. Now R4 has the packet, and since it's directly connected to the destination network, it can forward the packet to PC4. It does that by encapsulating the packet in a frame with PC4's MAC as the destination. This is the only time in the journey that the destination IP and MAC are of the same device. The destination IP is PC4's IP, and the destination MAC is PC4's MAC also. This process is very important to understand, but as I said, we will cover it step by step in another video. For now, just understand that the source and destination IPs of a packet do not change throughout the journey, but each time the packet is de-encapsulated and re-encapsulated, the source and destination MAC addresses are different. Okay, now I want to introduce another option when configuring static routes. We haven't configured any routes on R2 yet, so I'll just use it for this demonstration. When configuring static routes, instead of configuring a next hop, you can configure an exit interface instead. That means you specify which interface this router should send the packets out of, rather than telling it the actual IP address of the next hop.
Okay.
For example, if R2 wants to send packets to the 192.168.1.0/24 network, it should send the packets to R1. What interface should R2 send packets out of to reach R1? G00, because that interface is connected to R1. So here's the command. IP route 192.168.1.0, 255.255.255.0, G00. You can type out the whole interface name if you want, or just a shortcut like G00 is fine. Now, before we check the routing table, there is one more option. You can specify both the exit interface and the next hop. So if R2 wants to send packets to the 192.168.4.0/24 network, it should send packets to R4. And which interface should it send packets out of to reach R4? G01, because it's connected to R4. And what is the next hop IP address? It's 192.168.24.4, the IP of R4's G00 interface. So here's the command. IP route 192.168.4.0, 255.255.255.0, G01, 192.168.24.4.
Okay, I'm starting to build the formula in my head of
you can see how each route is
works.
displayed. An interesting point is that when you specify only the exit interface of the static route, it says the destination network is directly connected. Look at the route I've highlighted in blue. 192.168.1.0/24 is directly connected. That network is not directly connected to R2, but that's how it displays in the routing table when you configure only the exit interface. Static routes in which you specify only the exit interface rely on a feature called proxy ARP to function. This is usually not a problem, but generally you can stick to specifying next hop only, or both exit interface and next hop. Neither configuration method is necessarily better than the others. Just use whichever you prefer. Note that proxy ARP is beyond the scope of the CCNA. I won't spend time explaining it here. However, you should know that when configuring static routes, you can specify the next hop, the exit interface, or both. Okay, for the final...
That was so much information. Oh my god. But I think I understand it. It's all about, again, anything and everything that is technology is all about where it's coming from and where it's going. Sometimes it's about where it's going and where it's coming from, but it's the same. It's like saying 6 + 4 = 10, or 4 + 6 = 10. Like it's all the same thing, right? It still makes the circuit. It still makes the whatever you want to call it. So it's the destination, the mask, and then the next hop of how it's going to get there. Pretty crazy.
Topic, I'll introduce how to configure a default route on a Cisco router. I introduced the concept of default routes when explaining how a PC's default gateway works, but let's review. A default route is a route to O.O.O.O/O. /0 means that all bits of the net mask are 0, so none of the bits of the address are fixed. They can all change to be either 0 or 1. So O.O.O.O/O is the least specific route possible. It includes every possible destination IP address. If the router doesn't have any more specific routes that match a packet's destination IP address, the router will forward the packet using the default route. So a default route is often used to direct traffic to the internet. In the network below, R1 is connected to R2 and R3, which are other routers owned by the same business. More specific routes are used for destinations in the internal corporate network, such as destinations connected to R2 and R3. However, traffic to destinations outside of the internal network is sent to the internet using the default route. This isn't the only way to use a default route, but it's a very common use case. Okay, I added some IP addresses to the diagram, and also configured a couple static routes, which I'm not showing here. I then checked R1's routing table. First, notice the part I've highlighted. Gateway of last resort is not set. This means that no default route has been configured yet. Gateway of last resort is another name for default gateway. Now, in R1's routing table, there is a route to 10.0.0.0/8 with R2 as the next hop, and a route to 172.16.0.0/16 with R3 as the next hop. Perhaps these are networks used internally by the company. Now let's tell R1 to send all other traffic to the internet. Here's how to configure a default route. The structure of the command is the same as any other static route, but the network and net mask should both be all zeros, O.O.O.O. And that's it. R1 now has a default route. I checked R1's routing table. Let me point out a few things. First, here's the route, O.O.O.O via 203.0.113.2. Notice next to the S code indicating that it's a static route, there is an asterisk. What does that mean? In the code's legend, it says that the asterisk means candidate default. It means this route is a candidate to become the router's default route. It's possible to have multiple candidates. In this case, there's only this one. And here it states, gateway of last resort is 203.0.113.2 to network O.O.O.O.
Right,
so the route we configured was indeed selected. Okay, that's all we'll cover about default routes for now. The configuration is the same as a regular static route.
Was a lot of
Just remember that the
too.
network address and net mask are both O.O.O.O. We will use default routes in many future lessons as well, so you'll get more familiar with them throughout the course. Here's what we covered in this video. We reviewed...
Bro, we covered so much, and yet at the same time, I feel like it was like so small. There was so much information. I'm glad that I took the time to like read that stuff in over here, because I definitely understand it like so much better now. Now that I understand that the interface itself is the network. Very interesting. Okay, anyway, let's continue.
Connected and local routes by looking at the routing tables of R2, R3, and R4. Then we looked at static routes and how to enable PC1 and PC4 to communicate over the network. After that, we configured the static routes necessary for them to communicate. And here I've listed the commands to configure static routes. Usually, I just use the first option, specifying only the next hop IP address, but you should know the other options too. And the final topic was default routes. We looked at default routes earlier in the video when talking about PC1.
So we can do IP route, IP address. So we type IP route, and then we give the IP address like the destination, the mask, and the next hop. We can also exchange next hop to exit interface. Exit interface and the next hop, which is what we just did with default gateways.
And PC4's default gateways. And then at the end, we looked at how to configure a default route on a Cisco router. Okay, now let's go to the quiz to test your understanding of what we covered in this video. Here's quiz question 1. Which of the following commands configures a default route on a Cisco router? Pause the video now to select the best answer.
So it's got to be IP route 0000 because that's the IP address destination. And then if that is the destination, then that means that this is the subnet because none of the bits are being taken up. And then this is our next hop. Right? Crap, why do I think it's C?
Sir.
I'm pretty sure it's A, but something's telling me
Okay, the answer is A. IP route
Okay,
O.O.O.O.O,
I'm glad I went with what I knew.
10.1.1.255. When configuring a static route on a Cisco router, you cannot specify...
And this is just an IP address. You just kind of pulled this out of nowhere for it to be the default. Like, just to make the answer choices make sense.
the prefix length with a slash. You must write out the net mask. So B and D are incorrect. And in a default route, all bits of the net mask should be 0, as in A, so A is correct. In C, the bits are all 1, making it 255.255.255.255. That is not correct. Okay, let's go to question 2. Examine R1's routing table. Which interface will it use to forward packets destined for 8.8.8.8? That is
Google, by the way. Let's see here. Which interface will it used to forward packets to destination of 8.8.8.8. So, how do I know? Oh, there it is. So is it going to drop the packet because we don't have a destination?
Pause the video now to think about the answer.
I feel like
Okay, the answer is C, Gigabit Ethernet 02. The only route that matches destination 8.8.
Oh, because it can be sent to anyone.
8.8.8 is the default route. This route doesn't specify an interface, but it does state a next hop of 203.0.113.2. So if you look at the route for 203.0.113.0/24, you'll find it's directly connected to G02. So R1 will send packets destined for 8.8.8.8 to next hop 203.0.113.2 using the G02 interface. Okay, let's go to question 3. Examine the network below. Complete the graph with the static routes needed to allow PC1 and PC4 to communicate with each other. Pause the video now to think about the answer.
I need more caffeine. Like, straight up. This is so much information. Oh my god. Okay. So, this is our destination. We're connected. So then our next destination is going to be 4.0. Which means that our hop is going to be 13.3.
Answers.
I hope it doesn't give it
Okay,
to me
let's
all
check.
at once.
Note that the graph specifies R1, R2, and R4. We're not using the path via R3 this time. So each router in the path needs a...
Oh. I didn't notice that. So then it's going to be 12.2.
Route to 192.168.1.0/24 and a route to 4.0/24. R1 has a connected route to 1.0/24, so it just needs this path to 4.0/24.
Okay, good. So then the destination, the new destination is going to be going backwards because we need two-way communication. So it's now, this is going to be 0.1.0, and then this is going to be 12.1. And then R2 is going to want to go to over here because we're still trying to reach 0.4.0. So then that's going to be 32.4. Going back to 0.1.0. And then that's going to be 12.2.
24, with 192.168.12.2 as a next hop. As for R2, it needs this route to 1.0/24, next hop 12.1, and this route to 4.0/24, next hop 24.4. R4 has a connected route to 4.0/24, so it just needs this route to 1.0/24, next hop 192.168.24.2. Okay, with these routes on R1, R2, and R4, PC1 and PC4 should be able to communicate with each other. Let's go to question 4.
Watch out, people. I'm starting to understand.
Examine the following static route in R1's routing table. What command was used to configure this route? Pause the video now to think about the answer.
Okay. Is directly connected. Oh, S. So we had to go into interface G/1. Honestly, B's the only one that makes sense. But IP address is there. The only thing is that we don't have our next hop. But I don't think we need it. You never put the interface at the end of anything. It's B. It's got to be B.
Okay, the answer is D. IP route 172.20.0.0.
When did we talk about adding G0/1 on the end of something?
255.255.0.0 G01. The route states that the network is directly connected, so you might think it's a connected route added automatically by configuring an IP address, as in option B. However, that is wrong for 2 reasons. First, the route has the code S, so it must be a static route. A connected route would have a code of C. And secondly, 172.20.0.0/16 is a network address. You can't configure a network address on an interface, so the IP address command in option B would not work. When you configure a static route and specify only the exit interface, as in option D, it appears as directly connected in the routing table. Then, a technique called proxy ARP is used to find the next hop. Proxy ARP is beyond the scope of the CCNA, but feel free to Google it if you're curious. Okay, let's go to question 5. Examine the diagram below. How many static routes would you have to configure on R3 for it to know all destination networks? Pause the video now to think about the answer.
How many static routes would I have to configure on R3 for it to know other destination networks shown in the diagram? To know other destination networks? Just 2 routes because it can go here that way or it can go that way, right? Am I understanding that correctly?
Okay, the answer is D, 4 routes. R3 knows its connected networks, 192.168.13.0/24 and 192.168.34.0/24. For it to know all destination networks in this diagram, you would have to configure 4 additional routes to 192.168.1.0/24, 4.0/24, 12.0/24, and 24.0/24. Okay, that's all for the quiz and this video. I hope it was helpful. Thanks for watching. Before finishing this video, let me thank my JCNP level channel members.
Goats!
To become a member, please click the join button.
Tricky Mickey 1 2 3 4 5 6. That's so funny. That's so funny. Okay, I'm gonna go get more tea, and then we are going to do the packet tracers next. Because Lord knows I need caffeine. I need caffeine. Like, I need caffeine. Actually, no. Go back. Do the thing. Yeah. I got best of both worlds. Okay. Be right back. Let me go get some more tea here, and we're gonna do both packet tracers, not just one, but both of them. The configuring static routes and then troubleshooting static routes. I would imagine that the troubleshooting static routes is gonna be a pain in the butt. I'm actually very what is this comment? As a boy, Jeremy was that the world might go without understanding routing. Oh, okay, never mind. I misread that. Anyway, yeah, I would imagine that troubleshooting that stuff is gonna be a pain in the butt. But here we go. Tea time. I'm back. I guess I should have turned up the music for you guys. My bad. All right. So let's see here. All devices have no pre-configurations. Configure the PCs and routers according to the network diagram, host names, IP addresses, etc. Remember to configure the gateway on the PCs. You do not have to configure the switches. Okay. Starting to understand. Careful now. I'm understanding. All right, here we go.
Jeremy's IT Lab. This is a free, complete course for the CCNA. If you like these videos, please subscribe to follow along with the series. Also, please like and leave a comment, and share the video to help spread this free series of videos. Thanks for your help. In this lab, we'll get some practice configuring static routes on Cisco routers. Actually, there are going to be 2 labs for day 11 of this course. This first one, where you will configure static routes, and then the next one, where you will troubleshoot an already configured network that has some problems. Anyway, in this lab, we want to configure the network to allow PC1 and PC2 to ping each other. I haven't done any pre-configurations on these devices at all, so we have to go in and configure the host names, IP addresses, etc. first. I chose not to do any pre-configurations so that you can get some extra practice with the basics, as repetition is very important in getting used to the CLI.
Okay, so before we do anything, we're going to see what we can do on our own. So let's just get here and let's configure it. So let's go to enable, then config t, host name R1. Okay, so that's pretty good. Then let's look and see what the IP is supposed to be. So we want to go G0/1. Okay, that's where we're in. IP config 192.168.1.254. And that means our subnet mask is going to be 255.255.255.0 because we have a /24. So 8 times 3 is 24. Right? I'm so bad with counting by 8s. Yes. It is. Is it okay, so is it IP address? Actually, hold on. Ah. So then now we need to go to interface G0/0. Okay, that we're in now. And then we need this IP address. We're on the same subnet mask, so we're going to leave that alone. And we're going to go to 12.0. No, 0.1. Okay. Now, the reason we did 255 is because the router is the default gateway for this network. But this interface is not the default gateway of anything. It just needs to be connected to this. Okay. So then that means that IP route I don't remember. Okay. I'm sure he's going to configure each device at a time.
So let's do the basic configurations for each device as instructed in step 1. I'll start on PC1 first. Click on Config.
Yeah, I didn't do that. So we're just going to manually configure this 192.168.1.1. It should have... No, we don't need DNS server.
And the first thing we should configure is the gateway here. This is the address to which PC1 will forward packets, which are destined for a location.
Oh, the gateway, the default gateway. That's not going to be that. I just gave it the default gateway itself. Its default gateway is going to be 254.
Outside of the local network. PC1's gateway is R1, so I'll put in R1's IP address, 192.168.1.254. Next, click on Fast Ethernet 0, which is PC1's net.
And then this is its IP address, 1. There we go. It's all starting to make sense.
Network interface, and type in the IP address here, 192.168.1.1. And if you hit Tab, it automatically fills in the subnet mask for this Class C address, 255.255.255.0.
It's because I hit a bunch of space bars
exit out.
trying to start the video again.
Now, don't worry about configuring the switches. If you want, you can go in and turn off unused interfaces, set interface descriptions, etc. for extra practice, but I think you'll get plenty of practice just by configuring the routers. So let's go on R1 next. From the CLI, I'll use Enable to enter Privileged Exec mode. Then, configure Terminal to enter Global Config mode. Now let's set the host name with this command. Hostname R1.
I
Next,
did that.
I'll configure the interfaces. First, G01, which is connected to the internal LAN. Interface G01.
I did that.
Let's set the IP address. IP address 192.168.1.254, 255.255.255.0.
I did that.
And how about a description? Description to switch 1.
Ah, I didn't do a description. Okay. Description. I bet he's going to do... No, he doesn't.
Finally, let's enable it. No shutdown.
Okay, good.
Next, the G00 interface connected to R2. Interface G00. I'll set the IP address. IP address 192.168.12.1, 255.255.255.0.
Yeah.
Next, the description.
Crap, I put the description on the wrong interface. See, that's why it needs to say the interface that I'm in right there. Like... Oh. To router 2. Yeah, we'll call it R2. That's fine.
Description to R2. And let's...
Okay. So we're going to go to G0/1 interface. Description. To switch 1. No shutdown. Okay, so everything should be good. I did it in a weird order, but everything should be fine.
Let's enable it. No shutdown. Okay, let's check on the interfaces. Do show IP interface brief.
See, he says do show. Why? Sometimes he does do, sometimes he doesn't. Do show. Whoa, what was that?
Okay, you can see the IP addresses we configured. G01 is up, up, but G00 is up, down. That's not a problem. It's just because R2's G00 interface is still shut down.
Okay.
Now let's go on R2.
All right, now I'm going to try to do this all by myself. Enable. Config T. Hostname R2. Then we're going to go to interface G0/0. Okay, we're going to do no shutdown. And then IP address is 192.168.12.2 255 0. Yes. Description is going to be 2R1. Then we're going to get into interface G0/1. And oh shit, I gotta do that. I totally forgot about that. I need to take care of that paperwork. Don't worry about it. It's just something completely else in my mind. As my brain filters. Okay, now I'm in this interface. I need to do address. No. IP address. IP. Is it going to finish it for me if I do IP add? It does. Interesting. So then why doesn't it do it when I do show? And it won't do it. Interesting. IP address is going to be 192.168.12. No, that is not right. 0.13.02. Okay. No shutdown. Description. 2R3. Okay, let's see if we did it all.
Enter privileged exec mode with enable, then configure terminal. Set the hostname R2. Next, I'll configure G00, which is connected to R1. Interface G00. Set the IP address 192.168.12.2, 255.255.255.0.
I did that.
Then the description. Description 2R1.
Did that.
Now let's enable it. No shutdown.
Did that.
Okay, now I'll do the same on G01. Interface G01. IP address 192.168.13.2,
Yes.
255.255.255.0.
Yes.
Description 2R3.
Yes.
No shutdown.
Yes.
Okay, let's check on the interfaces.
Okay, hold on. Do show IP interface brief. I like it when it's like longer. Okay. Now that's down. And that's because that's what's connecting. Okay.
Do show IP interface brief.
Because that's...
Like we saw on R1 before, this interface is up-down because R...
Which I bet if I went back to here... And I did another... Up, up. We're good. We're golden. Okay, okay, okay. Okay. Enable. Config T. Host name R3. And then we're going to do interface G0/0. The IP address is going to be 192.168.13.3 255.255.255.0. Okay. No shutdown. Description 2R2 because that's what's going on. This interface goes to that interface. Okay. Let's do interface G0/1. IP address 192.168.13. No, that is not right. .3.255 because it's the default gateway. Okay. And we're going to put... Okay, hold on. No shutdown. Description. Default to PC 2. No, default to... No, don't put default. To switch to... Yes. Do show IP interface brief. We nailed it, boys. Which means we just need to go here, set the default gateway, which is 192.168.3.254. Static IP address. So that's going to be 192.168.3.1. Yes. All right.
R3's interface is still disabled, but the rest looks okay. Okay, next let's go on R3. Enter privileged exec mode with enable, then configure terminal. Set the hostname R3. I'll configure G00, which is connected to R2. interface G00. Set the IP address 192.168.13.3, 255.255.255.0. Then the description.
Hold on, let me pull this one up.
Description
Correct.
to R2. Finally, enable it. No shutdown. Okay, let's do the same steps on G01. Interface G01. IP address 192.168.3.254.
Nailed it.
255.255.255.0. Description to switch to. No
Yes.
shutdown.
Yes.
Let's check the interface's status. Do show IP interface brief. Okay, looks good. And the interfaces we configured are both up. Finally, I'll configure PC2. Click config, then set the gateway here, which should be R3's IP address.
Yes.
192.168.3.254. Then click on Fast Ethernet 0 and set the IP address here. 192.168.3.1 and hit tab to autofill the subnet mask.
Yep.
Okay, so we've done the pre-configurations. Just some review of basic commands for practice. Now, let's get to the main point of this lab. Configuring...
Okay, I'm going to go to the bathroom real quick. I'll be right back. Okay, I'm back. Sorry about that. But I'm now ready to move on. I also kind of reviewed the stream a little bit, and I saw that the music could be just a tad, just a touch bigger. Okay. So now what we need to do is we have to add these static things. Everything we've done up until now has been review, which is kind of crazy because it's half the video. Half the video was half the packet tracers review.
Static routes. Before starting, let's think about what static routes we'll have to configure. We need two-way reachability, so PC1's ping can reach PC2, and then PC2's reply can reach PC1. R1 is already connected to the 192.168.1.0/24 network, so it just needs a route to 192.168.3.0/24. Likewise, R3 is already connected to 192.168.3.0/24, so it just needs a route to 192.168.1.0/24. R2, however, is not connected to either of those networks, so it will need routes to both. So that means a total of 4 routes need to be configured. 1 each on R1 and R3, and 2 on R2.
Okay.
Let's go on R1 and configure the first of the routes. We have to be in global config mode, so I'll type exit to get out of interface config mode. Configure the route with this command, IP route, and let's use the context-sensitive help to check the options. So it says destination prefix, meaning the network address, which is 192.168.3.0.
Okay, so this is the part that I was struggling with earlier. Is that it's IP address, and then it's 192.168.3.0. Because that is my destination. That's where I'm trying to go. And then the subnet mask is 255.255.255.0. Yes. And then what address goes there? The next hop. So the next hop. What's the next hop going to be? The next hop's going to be 192.168.12.2. Because this should be the next hop.
Use the context-sensitive help again, and next is the mask, which is 255.255.255.0, since it's /24. Next, we can specify the forwarding router's address, which is the IP address of the next hop router, or we can specify the exit interface. All of these options are interface types.
Interesting.
I'll specify the next hop address of R2, which is 192.168.
So it doesn't have to be the next hop. It could be any of these things. The forwarding router's address, which is the next hop. The dialer, I don't know what that is. Something to do with Ethernet. Fast Ethernet, Gigabyte Ethernet, loopback, null interface. Wow. I kind of know what some of those are.
12.2. If I use context-sensitive help again, you can see there is another possible option.
District metric for this route. Well, I was right.
Distance metric for this route. I'll talk about this option in a later video, but this CR down here means we can just enter the command as is. Okay, now let's check out R1's routing table.
Invalid? Oh, because I misspelled fucking address. It's still saying it's not right? What? Oh, because it's IP route. There we go.
IP route. there's the...
Okay, so let's do it. Do show IP route. Okay. Yes. There's our connected. .1. Yes, .24. So that's here is directly connected. Gigabyte Ethernet 1. Yes. And then we have the L, which is the local. Okay. Okay, let's keep going.
Static route we configured, as indicated by the S here. You can also see the configured and local routes for R1's two interfaces. Remember, the local route is the actual address configured on the interface, with a /32 mask, so it specifies just that single address. And then the connected route is the network address of the network the interface is connected to. Okay, R1's route is done. Let's go on R2. Again, exit to get out of interface configuration mode. Let's configure the route to 192.168.1.0/24. IP route 19.
Okay, now hold on. Let's see if I can do this myself. So enable config T IP routes, and we need 192 because this is our destination. Our destination is still that 192.168.3.0. Okay, and then this is our next hop. Our next hop is going to be 192.13.3. Let's see if we're correct.
92.168.1.0, 255.255.255.0, and then just a...
Because it's got to talk backwards. It's got to go back. But is this correct to do the other one? Because there's two that we're going to have to do, right? Oh, I forgot that you can't do that. So, 0.1.0. So that way we can go backwards. So then what's our next hop? What's our next hop going to be?
To practice the other option, I'll specify the exit interface instead of the next hop IP address, G00.
The exit interface. So does that mean that I have a choice? I can either put G00 because G00 has an IP address, or I could just put that IP address, which would be 192.168.12.1 because of this right here and this. So then now does that mean that the next thing that we're going to do is IP routes? What our destination was 192.168 point, what is it for? 0.3.0. Okay. And then our destination is going to be, well, we have it configured. So can I not just use G0/0?
This message comes up, but you can ignore it. It says, if not a point-to-point interface. However, this is a point-to-point interface, meaning it connects only to one other device. This is different than, for example, many routers connected to a single switch, which we would call a shared segment. Anyway, don't worry about that for now. You can just ignore this message. Okay, next let's configure the route to 192.168.3.0/24. IP route 192.168.3.0, 255.255.255.0, and this time let's do the next hop IP address, 192.168.13.3.
Okay. I think that's correct. But for the sake of doing it correctly and not knowing certain factors, but I'm pretty sure that I could do, because that's the IP address of that interface. But anyway, I digress. 92.3. Okay, so that means that should be done, right?
Okay, let's check the routing table.
I guess I could have done it and checked the routing table and then gone back and fixed it. Okay, do show route brief.
Do show IP.
Do show IP.
IP route.
Dang it. Okay. Is directly connected. Static. Yes, that's what we did. Is directly connected. This is not. So that's the next hop. Okay. Wow. Is this actually starting to make sense?
Okay, here are the two static routes, and the connected and local routes for each interface. Looks good. Finally, let's configure R3's static route. Type exit to get out of interface config mode.
The reason I don't hit X is because it's been too long, so it just kind of timed out and logged me out and whatnot. Okay, enable. We're going to see if we can do this ourselves, boys. Enable config T. And then we're going to do IP route. The IP address that we're trying to get to, which is 192.168.3.0. No. We need to do, well, I don't think that there is a correct order that it has to be done in, but I'm going to do it in the order that the video has been doing it. So we're going to trail it back 1.0. So that means our next hop is going to be 192.168.13.2. That should be it.
And let's configure a route to 192.168.1.0/24. IP route 192.168.1.0, 255.255.255.0, 192.168.13.2, setting R2 as the next hop.
Which means that IP routes, and this is where we're trying to go to. We're trying to go to 192.168.3.0. Okay. And then we have our next hop, which should be 192.168.3.254? Question mark?
Let's check the routing table. Do show IP route. Okay, looks good. One static route, and the connected and local routes for each interface. Now let's go on PC1 and try out that ping.
Okay, we don't need to do this because we are already directly connected to the network. So now if we go here, desktop. Is it, wait. Do we want terminal or command prompt? We want command prompt. So ping 192.168.3.0. Yeah, because I just pinged the network. I didn't ping the PC. I pinged the wrong thing. So it's timing out. Oh. Oh. Now if I do it again, it shouldn't have any losses. That's what I'm talking about. We did it, boys.
Click on desktop, then command prompt. Okay, so this is the moment of truth. The first ping might fail due to ARP, Address Resolution Protocol. But once ARP is finished, the rest of the pings should work if we configured everything correctly. Let's try. Ping 192.168.3.1.
That means that he pinged it for the video, whatever, and it didn't work. And it didn't work because something was going on with ARP on his packet tracer. And so then he didn't want to see all of it. He didn't want to show all of his troubleshooting, which is fine. And I am doing a stretch. I could be totally wrong. He might have just wanted to hit enter a bunch of times, you know? But I know, as someone who's made videos about that stuff before, I've had that happen before where I'm like, well, this should happen. Why is this not working? You know?
Okay, looks like PC1 is able to reach PC2, and PC2 is able to reach PC1 with its reply. We have successfully configured static routing. That's all for this lab. Thank you for watching. Please subscribe to the channel, like the video, leave a comment, and share the video with anyone else studying for the CCNA. If you want to leave a tip, check the links in the description. I'm also a Brave verified publisher and accept BAT or Basic Attention Token tips via the Brave browser. That's all for now.
Whoa, no, what happened? Okay. This is the next one. Okay, one more packet tracer and then we're going to be done, boys. Ugh. Okay, so PC1 and PC2 are unable to ping each other. There's one misconfiguration on each router. Find and fix the misconfiguration. You have successfully completed the lab when PC1 and PC2 can ping each other. So, what we're going to do is we're going to go in here. Enable. Config T. And we're going to go to IP route. Show IP route. Do show IP route. Okay. So let's see what we have here. We're on router 1. Router 1, we have 0.1.0 verbal subnetted 2 subnets. Yes. And yes. Okay. Directly connected to 12.0. That shouldn't say 12.0. That should say 12.2. Okay, I think I just found the first one.
Welcome to Jeremy's IT Lab. This is a free, complete course for the CCNA. If you like these videos, please subscribe to follow along with the series. Also, please like and leave a comment, and share the video to help spread this free series of videos.
I'm pretty sure that's the error, but we're going to double check.
You may recognize this network topology. This is the same network we configured in the previous lab.
One.
However, this time there are a few configuration errors, so PC1 and PC2 are unable to ping each other.
Light work, ain't nothing we can do.
As the lab instructions say, there is one misconfiguration per router, so we have to find and fix the misconfigurations. Troubleshooting labs like this are great practice for the CCNA. Troubleshooting helps test your knowledge of the concepts, and troubleshooting questions may also appear on the CCNA exam itself. I highly recommend you try to complete this lab yourself first. If you watch the video before, you will already know what the problems in the network are, and you won't practice your own troubleshooting skills.
Well, we're going to do it as we go.
Okay, before we get started troubleshooting, we should confirm the problem. PC1 and PC2 are not able to ping each other. I'll go on PC1 and try to ping PC2.
I guess technically, no, I did not do that. I'll do that really quick. Ping 192.168.3. What was it? 1. Request timed out. Oh man, request timed out. Oh god, we're losing packets. Oh god, I'm losing packets. All right, yeah, of course, it all timed out. We knew that was gonna happen. I'm losing packets. That's fun.
Okay, let's send that ping. Ping 192.168. This configuration on a Windows PC. Use the command ipconfig. Here you can see the IP address.
Ah, no, okay, I didn't think about that. He said that the problems were going to be on the routers. I didn't really IP config. What is happening? What? Oh, there's no space. Okay, let's double check our address here. Okay, IPv4 address is correct. Our default gateway is correct. So the PC is fine. That means that the problem has to be the routers. The routers are dropping packets. You don't want to drop packets. You drop packets, you're going to have a bad time. Okay, here we go.
Address, subnet mask, and default gateway. If you want more detail, use the command ipconfig/all. This gives more information, such as the physical address. What is the physical address? Well, it's the MAC address. Okay, let's see if we can ping the default gateway. Since to reach other networks, we need to be able to reach the default gateway. Ping 192.168.1.254.
Done here.
Okay, no
well,
problems
and
here.
We knew that was going to happen because the default gateway was set correctly. If the default gateway was set correctly and we were not able to ping it, that would lead me to believe that the problem is the switch or the cables, not a configuration, not a virtual configuration, but a physical one.
Let's go on R1 now and see if we can find the issue. Enter privileged exec mode with enable. First, I'll check if the interface configuration is okay. Show IP interface brief.
Okay, I didn't. Damn it! I didn't do this.
The addresses are correct, and both interfaces are up. So the interface configuration is fine.
I'm telling you, I'm really.
Let's check the routing table. Show IP route. Here's the static route for the 192.168.3.0/24 network. But can you see the misconfiguration? It says via 192.168.12.3.
Oh shit!
But actually, the next hop address should be 192.168.12.2.
It's right here. So why did I think that was it? Because I thought this was the network, but I guess it's directly connected, so that would be fine. So does that mean that's as simple as IP routes where we're trying to go to, which is 192.168.3.1, right? Yes. 255.255.255.0. And then our next hop, which is 192.168.12.2. Correct?
which is the IP address of R2's G00 interface. Let's check it in the running config. Show running config, and then I'm going to filter the output by using the pipe symbol, include, and then IP route.
Bro, we've never even gone over that. I didn't even know that was called the pipe symbol. What do you mean the pipe symbol? What? Okay, show running config, include IP routes. IP route, and there it is. I didn't even know that was possible. What?
Here you can see the configuration statement. I'm going to right-click to copy it, and then go to Global Config Mode, Configure Terminal. Now I'll paste in the configuration statement, and use the keyboard shortcut Control-A to go to the beginning of the line, type no, followed by a space, and then hit enter. And that deletes the configuration statement. Let's check.
Oh, it doesn't just override it, you have to delete it. I didn't know that. Oh. Okay. Okay, so then now IP routes. Yes. IP route 192.168.3 point. Yeah, point 1, right? That's where we're trying to go to.
Do show running config, pipe, include IP route.
And now we're checking to see if it's dead.
Okay, it's gone. Now I'll paste in the configuration statement once more and change this 3 to a 2. I'll use the up arrows.
So our destination is the network, not necessarily this. Okay. That makes sense, kind of. We have definitely gone over a bunch of material today. It's been a really good study session. Okay. So then do show IP route. Damn it. And it's fixed. Okay, I doubt that it's going to be the same problem every single time.
To go back to the show running config command, and now you can see we have the correct configuration statement. Let's check the routing table one last time. Do show IP route. Okay, there's the correct route. So we have fixed the problem on R1.
Okay.
Now let's move on to
R2 and let's see what's going on with R2. Enable config T. Do show IP route. So let's see if we can deduce what's going on. So 192.1.0. That's our static. 192.3.0 is directly connected. It's not directly connected. 12. Oh, I didn't check to see if it was show running config. Do show running config. No. Show IP interface brief. Do show IP interface brief. Okay, everything's fine. I just wanted to, because I didn't check this last time. I just wanted to check it. So now let's go back to this bad boy. We are not directly connected to 168.3. That is where we're trying to get to. Maybe we are. No, because that interface is not that. Then we have 12.0. Two. Ah. No. Okay, I think that the problem is this one. I'm not certain though.
R2.
I don't think there's anything else I need to check. I checked to see if things are up.
Enter privileged exec mode with enable, and let's check the interface configuration. Show IP interface brief. The IP addresses are both correct, and the interfaces are up, so no problems here. Let's check the routing table. Show IP route. We have two static routes as expected. 192.168.1.0/24 via 192.168.12.1 is correct. And 192.168.3.0/24 with an exit interface of gigabit Ethernet 00. There's our problem. To reach the 192.168.3.0/24 network, R2 should use the gigabit Ethernet 01 interface, not 0.
Oh. What?
There's our problem. To reach the 192.168.3.0/24 network, R2 should use the gigabit Ethernet 01 interface, not 00. Let's see what happens if I enter the correct route without removing the incorrect one. Configure terminal, IP route 192.168.3.0, 255.255.255.0, G01. Do show IP route. Okay, you can see both routes are kept in the routing table. The second does not override the first. Because both are in the routing table, this means the router will load balance over the two routes, sending some packets out of G00 and some packets out of G01.
Boo.
Sometimes load balancing is a good thing, but in this case the G00 interface is totally wrong, so we should remove that configuration statement. Do show running config, pipe, include IP route. Okay, right-click to copy, right-click to paste, hit Control-A to skip to the beginning of the line.
Whoa. Look at that. Look, he's a pro. He's a pro. Do show run include IP route. Copy. Paste. Control A. No. So what I need to do is change that to a 1 because we want it to come out of the 1, right?
And type no. Let's see if the route was removed from the routing table. Do show IP route. Okay, now we only have one route to 192.168.3.0/24, using the correct interface, G01. Finally, let's look for the issue on R3.
Okay, so far I've been wrong on all of them. Boom, boo. Do, 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 do. Enable config T. Do show IP brief. Okay, everything's up. We should be good. Do show IP route. Okay. Let's inspect things. So last time, the first time I missed it because I had the IP address wrong. Second time I missed it because I was only focused on IP addresses and not the actual interfaces. So this time we're going to look at all of them. Okay. We don't have a static address. That might be the issue. Okay, that's where we're going. 0 is out of gigabyte 1. Okay. 23. Where do we get 23 from? I don't know where we got 23 from. It's saying that 192.168.23.0 is directly connected to 00. But that's not right. I think the IP address is wrong.
First, enter privileged exec mode with enable. And once again, I'll check the interface configuration first. Show IP interface brief.
Hey, that's what we did.
Both interfaces are up. However, there is a misconfiguration here. R3's Gigabit Ethernet 00 interface should have an IP address of 192.168.13.3, not 192.168.23.3. Let's fix that. Configure terminal, interface G00.
Now, hold on. Do we have to say no? Do we have to release the IP address, or is it going to override?
Now, unlike when configuring routes, we don't have to remove the current configuration first.
That's what I wanted to know. So that means, so I was right. So this is not correct. That needs to be 192.168.13. Point 0? No, 0.3.
If we enter a new IP address, it will overwrite the current IP address. Let's see the config before and after.
Okay.
Do show running config. Okay, here's the incorrect IP address.
Yeah.
Now let's configure the correct
Bad.
IP address.
That's bad.
IP address 192.168.13.3, 255.255.255.0. Let's check the config again. Do show running config. As you can see, the previous configuration was automatically overridden. We did not have to delete it. Okay, since we are told there is one misconfiguration per router, we don't have to check the routing table, but let's take a quick look anyway. R3 should have a static route to the 192.168.1.0/24 network. Do show IP route.
It's fixed.
There it is, via 192.
Okay, so I caught the mistake. I just didn't catch it the first time when I was looking at this stuff. I didn't catch that. I was mainly looking to see if things were up or down. So I guess it goes to show you that you need to look at literally all things, including even looking at this stuff, because even though I didn't catch it here, because I wasn't technically looking for it, when I looked here, I did catch it. So, you know, all about doing your due diligence.
168.13.2, which is R2. Now that we have fixed the misconfigurations, let's go back on PC1 and try out that ping again.
Okay.
The first ping or two might...
Command prompt. That ain't good. Oh, that bad. Okay. One made it. Sometimes when a network or there's been an issue, that's why it sends like 4, is that it might take a second for it to reestablish connection. And out of those 4 replies, only 1 might make it. And then if you run it again, they'll all make it. Okay. But in reality, all you need is 1 to prove that there's connectivity.
Might fail, but after that, they should all succeed. Let's give it a shot. Ping 192.168.3.1. Okay, so after finding and fixing the misconfigurations on R1, R2, and R3, PC1 is now able to ping PC2. That's all for this lab.
Okay.
Thank you for watching. Please subscribe to the channel, like the video, leave a comment, and share the video with anyone else studying for the CCNA.
He is great. If you have not subscribed to him, or if you're trying to like get your CCNA or want to know anything about networking or anything, like he is absolutely phenomenal. Like I'm on day 11 of his like free CCNA work, whatever. It is absolutely phenomenal. 100%, 10 out of 10, would do again. Can't praise these videos enough. They are so intuitive. They're so good. They're so good. Okay, we are gonna call it. We're gonna call it there. Please go ahead if you like if you like hanging out with me and you like studying with me and stuff like that. Please go ahead and give me a little bit of love, a little bit of you know, like, subscribe, and all that good stuff. I will say that we are going to add a review session. Okay, every Sunday on this channel only, we are going to review what we have previously learned. Okay, we're not going to cover any new material. We are only going to do what we previously have learned in the past videos of the CCNA stuff with Jeremy. Okay, so if you're wanting to watch any of the other previous streams, you definitely can. They're all right here. They are also going to be in a playlist. Okay, I do have some videos that I'm working on to try to get them pushed out to help with like the Network Plus labs and stuff, because I know that a lot of people were finding that helpful. So I'm in the process of like getting that stuff done and whatever. I'm just trying to balance the new job and the new life in studying and all that stuff. You know what I mean? But we will start reviewing on Sunday mornings at 8 a.m. We might even push it to 7 a.m. I don't know about that one. Okay. But it's only going to be reviewing what we've already done. It will not be any new material. Okay. So that's what's going on with that stuff. If you enjoyed the video, if you're enjoying the stuff, please like the video, share it with a friend, subscribe to the channel, all this stuff. I do have a few other videos that aren't lab based, that just kind of explain some topics and things like that with some basic networking and tech stuff and whatnot. So if you like that stuff, hit me up. Okay. You can find me on Instagram and all that good stuff as well. If you have any questions about anything, don't hesitate to ask. I'll do my absolute best to answer it for you. And if I can't answer it for you, I will find you resources so that way it can answer it for you. Okay. But that is all I have. Don't forget to work with what you've got and build what you need. And I will catch you in the next one.